All right, let's jump right in. Think about your morning routine. The coffee machine that brewed your coffee, the car you drove, maybe even the watch on your wrist. What do they all have in common? Well, every single one has a tiny, hidden computer inside, a little brain making it all happen. Today, we're going to pull back the curtain and find these invisible computers.
I mean, we hear the word smart thrown around all the time, right? Smart devices, smart homes, smart cars. But what actually makes them smart? What's going on inside a smart thermostat that's different from the old dial on the wall? That's exactly what we're going to figure out. We're going to look under the hood.
So let's open the box. A modern car is a perfect example. You might think it has one central computer, but that's not even close. A new car can have over 100 of these little specialized computers, each one handling a specific job. From the engine timing to the airbags to your infotainment system, it's wild. And it's not just cars. These things are everywhere. Let's start tracking them down.
Okay, section 1, inside the smart device. So where are these things hiding? You might be surprised. The answer isn't just in your phone or your laptop. Nope, it's pretty much everywhere.
Seriously, they're in places you'd never expect. Think about the massive 5G towers that connect our world, or the tiny little IoT sensors monitoring everything from air quality to soil moisture. They're the brains behind the robots in factories and the engine control unit in your car. And yeah, they're in your living room too, running your smart TV, your Wi-Fi router, even your microwave. They are absolutely ubiquitous.
All right, so they're everywhere, we get it. But what are they really? Like, what are the physical pieces, the building blocks that make up every single one of these embedded systems?
Okay, let's break it down. At the heart of it all, you've got a processor, usually a little guy called a microcontroller, or MCU. That's the brain. It needs memory, of course, to store its instructions and any data it's working with. Then you've got input and output, or I/O. This is how it talks to the outside world. Think of some I/O like simple on-off switches, while others are for more complex data. And how does it interact with the physical world? Through sensors to see and actuators to do things. And naturally, the whole thing needs a steady power supply to keep it running.
But here's a really cool thing. These parts don't always have to live on a single chip. In fact, a really smart strategy is to build a team of specialists. So, for our running example, imagine this. You've got an STM32 microcontroller. Its one job? Reading sensor data with incredible speed and precision. It's a specialist. Then it hands that data off to an ESP32, which is a total pro at Wi-Fi communication. The ESP32 then beams that data over to a Raspberry Pi, which is way more powerful and great for running a nice user dashboard. See, each part plays to its own strengths. It's teamwork.
So we've got the hardware, the physical body of the system, but on its own, it's just a pile of silicon and plastic. What gives it life? What tells all those parts what to do? That's the software. You can think of it as the system's soul. And this software comes in different layers of control. At the very bottom, the most direct level, you have bare metal programming. This is where your code is talking directly to the hardware, no middleman. A step up from that is a real-time operating system, or RTOS. Now, an RTOS is a lightweight OS that is absolutely obsessed with timing. Think about a car's airbag system. It must deploy in milliseconds, no excuses. And RTOS guarantees those critical tasks happen precisely on time. Then, for the really complex jobs, you'd bring in the big guns, a full version of embedded Linux. And just to give you a taste of what bare metal actually looks like, check this out. It might look like gibberish, but this one little line of C code is how you turn on an LED on a specific microcontroller. You're not using fancy libraries or anything. You are directly manipulating a specific hardware register on the chip. There is nothing in between your command and the silicon. It's incredibly fast, super efficient, and very, very low level.
And this brings us right back to our multi-board example. Now it makes sense, right? It's all about using the right tool for the job. Our STM32, which just needs to read a sensor as fast as humanly or siliconly possible, perfect for bare metal. The ESP32, which has to juggle Wi-Fi connections and sensor tasks at the same time, it needs an RTOS to manage all that concurrency. And the Raspberry Pi, which is running a whole web server, well, that needs a full-blown operating system like embedded Linux to handle all that complexity.
Okay, so we've covered the hardware and the software. We get the components. But how do you actually go from a great idea to a finished, working product? What's the blueprint for making one of these things?
Well, it follows a pretty logical workflow. You always start with requirements. You have to know exactly what the device needs to do before you can build it. Then you move to design.
This is the big picture architectural phase where you choose your hardware. After that comes development. That's when you're actually writing the code, compiling it, and flashing it onto the chip. And this next part is absolutely crucial, test and debug. Because trust me, nothing works perfectly the first time. Finally, you integrate everything, bringing all the different hardware and software pieces together into one cohesive working system.
And I really want to stress the difference between design and development. It's a super important distinction. Think of it like building a house. The design is the architect's blueprint. It's the plan, figuring out where the walls go, what materials to use. The development is the construction crew actually building the house from that blueprint. One is the plan, the other is the build. You need both to succeed.
All right, we've looked at the hardware, the software, and how they're made. Now it's time to put it all together. Let's really nail down the answer to the big question. What is it that truly makes a system embedded?
So what's the defining DNA here? What really separates, say, a smart thermostat from the laptop I'm using right now? I mean, they're both technically computers, aren't they? Well, yeah, but it comes down to a few key defining characteristics.
First off, an embedded system is a specialist. It does one specific job, and that's it. It's also resource constrained. It's built with just enough CPU power, just enough memory, and it's super careful with its energy consumption. Many of them have to operate in real time, where responding within a strict time limit is non-negotiable. The software and hardware are tightly integrated. They're basically made for each other. They're designed for insane reliability to run 24/7 for years without failing. And finally, they often have a minimal user interface, or none at all. They just run headless in the background, doing their job.
So let's put it all side by side to make it crystal clear. Your laptop, it's a general-purpose system. It can run a web browser, a video game, a spreadsheet, anything you throw at it. A smart thermostat, an embedded system, has one job. Your PC has high-performance modular hardware you can swap out. An embedded system has custom hardware, limited to exactly what it needs. And while your PC doesn't really care if an email takes an extra second to send, for many embedded systems, that real-time performance is absolutely critical.
So here it is, the grand definition. An embedded system is a special-purpose computer. It's built into a larger device to perform one, or maybe a few, dedicated functions, often in real time. It's the hidden, dedicated brain that just makes our world work.
So now you're in on the secret. The world is absolutely packed with these invisible computers, and now that you know what to look for, you're going to start seeing them everywhere. The only question is, which one will you notice next?